Okay, so this is what stands between you and the lightning talks. Adventures in CORFU, testing and verifying chain repair protocols using Concuerror, and this is joint work with Stavros and with a guest star that you will find out during the talk. I would like to start with a bit of geography. This is Corfu Island in Greece. It's in the northwest of Greece, pretty between Greece and Albania, as you can see on the map. It's a pretty big island, and immediately below it to the south, there are the Paxos Islands. Paxos is, as we heard, is quite expensive actually, which is true. Corfu is not so expensive. It's not a very cheap place either, but it's not so expensive as Paxos. It's a very picturesque place. And I would love to just tell you that I went there and I had very beautiful mornings, drinking my coffee and looking at something like this. And then in the lunchtime, I had I very much like to actually have ouzo for lunch, this is true, in the summer only in Greece, looking at such beautiful scenery. And in the evening, you can have a very nice lunch in places like that one. But as a matter of fact, this talk started after vacations. When I came back, my student, Stavros, informed me of a tweet that he had seen while he was on vacation. And this tweet was this one. I was all ready to have a celebratory new algorithm works tweet. Then the DPOR model execution with Concuerror found an invalid case. Ouch. And it so happens actually that I'm not in Twitter. I don't really care about Twitter. And over the last few months, I came to realize that I probably should not pay too much attention on what important Americans write on Twitter. But this one is actually special. It's a very knowledgeable person, part of our community. Is Kotlik Fritz, who describes himself on Twitter as a jack of many bit-centric trades, many of them Erlang flavored. And he has worked in a number of companies and has done quite nice projects and software tools. And you can see here what he has been working on. In particular, just in case you did not know it, he was the one that contributed the first version of dtrace that you can support that exists in OTP. And these days he is working on CORFU DB. And that's where he is working at VMware, and he is working in a project called CORFU DB. And that's where the connection of adventures in CORFU comes in. It's not so picturesque as the pictures I just showed. So here's where my actual talk actually starts. I will talk briefly about chain replication and chain repair. Then I'll talk about systematic concurrency testing and the tool we have built on which is called Concuerror. Some of you may have seen it in other talks or in the tutorial yesterday. And I will do a very, very, very short demo. And then we'll try to discuss how we actually used Concuerror to verify algorithms and protocols that people at VMware have been designing actually. So it wasn't like they took an existing protocol out there and we just verified it. And as part of this process, actually, we found that we could improve certain things on Concuerror, and I will describe also about these things. So let's start with basics. What is chain replication? Who has heard of chain replication here before? Some people, but not so many. It's actually not a particularly difficult algorithm to understand how it works. It's a variant of master-slave replication. There is a strict chain order, and to just simplify things, let's say that we have 3 servers, a head server, a middle server, and a brick server. So all the write requests start from the head server, and they propagate slowly to all the other servers. And a write is only appears only when it has propagated to all the servers, it has gone to the tail. Okay, so that's when we can all agree that the write exists there. So since things are happening in that order, all the read requests should actually be serviced by the tail server. So all the read requests happen at the tail server. So this is fault tolerant in the place of failures, and of course you have to worry about how to repair this chain in the case that failure happens. So if you want, all the reads are sequenced at the tail. If this is linearizable at any point, if you want linearizable reads, you can read from anywhere. And dirty reads, you can read at the head or middle if you want. If you have dirty thoughts, you can do that sort of thing. I not recommend it, but anyway. So let's say that we want, some failure happens, and we want to repair this chain. So let's say that we have a chain of just 3 servers, just to simplify things, and one of them crashes. Let's say the blue one crashes. And we are left with the remaining 2 servers in the chain that you see here with the cyan and whatever other color that happens to be on your screen. I cannot see it from here. From here, it looks like a brick color. So you copy the tails update history to now the repairing node. And one way of doing chain repair in the chain replication protocol is to put that repair node at the end. And once all the update history has gone to the repairing node, then you have restored the chain. Now, while the chain is being restored, all the reads get serviced by the tail, but not the repaired chain, the repaired server. Okay, in this picture is the middle, the brick color, the reddish color server that services all the reads until the chain is fully repaired, in which case now there will be a point of where the chain will be declared repaired, and now the green one will be the new tail that will be servicing all the reads. Now, this is an old algorithm published in Usenix many years ago, and it has been implemented in various systems, among other systems in Hibari DB, which is one of the database systems that Scott has been working while he was working in Japan. And Hibari is sort of similar to this one, but places the repairing node directly on the chain, and reads go to the old tail here. Okay, so so you can have some variations, and you can have various protocols of repairing this chain when things go bad. So there is a new system out there, initially developed by Microsoft Research, called CORFU. These days is developed by VMware, and it's called CORFU DB. But the main idea is that it's a variant of chain replication, but it has 3 changes. The responsibility of replication now is moved to the client, not to the servers. And actually, clients do not communicate in any way with each other. And all the CORFU servers implement write-once semantics. So you never update values here. And the protocol or the CORFU identifies its chain configuration with an epoch number. And all clients and servers are aware of this epoch number. The servers reject clients with a different epoch number. And a server temporarily stops service if it receives a newer epoch number from the client. So everybody has a chance to actually go to the new epoch and continue from that point on. Okay. So the engineers at VMware, what they were doing, they were designing chain repair algorithms for CORFU. And of course, since Scott is one of the engineers that had worked on chain repair algorithm before, he said, okay, let's try to do the Hibari way. Let's try to put the repaired node at the end. So that's one of the protocols that he first tried. So they were sitting around there in a whiteboard or a blackboard, or I don't know what room they were discussing really. And they were trying to see whether this Hibari way of fixing the chain will actually work. So they drew something like this one. Let's say that they repair during some epoch 5, let's say. And we have a client that is writing a new value to the cluster for a data with an old value. So this new value, of course, propagates from the head till the end. So it's conceivable that during the point of epoch 5, you will have the new value on the head. Then in the previous tail server, you might have an old or a new value. And of course, in the one that you are repairing, you will have an old value. Okay. So while these new values get propagated, let's say that somebody decides that it's time to change an epoch. And in the new epoch, when you change, you will have also, of course, a new value in the previous chain that you didn't need to repair. And in the tail in the new tail, you might have an old or a new value, okay, depending on whether the new value has arrived there or not. So if it is the case that somebody sees a new value at the previous tail and an old value now in the new epoch, this is a violation of the linearizability property. And actually, this is possible. You can sit down and think really hard and find the case where this is actually happening. And that's what the engineers at VMware found, okay? So that the Hibari way of fixing chains, of repairing chains, doesn't work for CORFU. It works for Hibari, but doesn't work for CORFU. So I don't know exactly how many days they've spent in this, or perhaps an hour, or it doesn't really matter. But they found the case that this didn't work. So then let's say, okay, let's try to have some other protocol. But at that point, Scott, who knows our work quite well, said, okay, this is totally pointless. Why do we have to spend all our time thinking about these algorithms and trying to find counterexamples? Why don't we just program these algorithms as concurrent programs and have a tool like Concuerror to try to see if it can find counterexamples? So and of course what it started is with programming this particular one, that they knew it was buggy. So if Concuerror can find the error here, then at least this gives some confidence that the tool is not totally crappy. Okay, it can find the error, so at least, you know, what they have done, spending time thinking, can be automated. And then perhaps they can program the other protocols that they had no clue whether they are correct or not, also in the tool, and have the tool find the counterexamples. Okay, that's exactly what it did. And this is exactly the adventure I'm telling you here. But now I have to take a detour and discuss how Concuerror works and actually how stateless model checking works. Stateless model checking sometimes is known as systematic concurrency testing. This is testing on steroids. You test, you really test very systematically, but very, very, very systematically, until you are sure that actually you have explored everything. Okay? So this is not quick check-like testing. This is not pulse-like testing. This is verification. Okay? You have a guarantee that you have explored everything. If it terminates, of course. Okay? But at least if it terminates, you have a guarantee. It's not like, oh, it didn't find me any errors. Now what? So how does it work? Let's assume that you only have one scheduler. Back when I grew up, where we had single core systems. So then you run an arbitrary execution until it finishes, and then you backtrack to a point where there is an alternative, where there could be some other process that could be scheduled there. And you pick, let's say, the latest of these backtracking points. And from there on, you continue with another execution. And you keep repeating that until all the choices have been explored. It conceptually is as simple as that. Okay? Now, let's do it in an example here. So let's have some Erlang program. It's a relatively simple Erlang program. It's a concurrent one. We have a main function, and which spawns two new threads, P1 and P2. And this P1 and P2 are calling some code from some other module, the good, the bad, and the ugly module. In this example, I will only use the good and the bad. And then there is a receive statement that checks whether it has received good, and then does some more computation, and things are okay. If it receives bad, will do some more computation, but a bug will be hit. So it will be, I'll show this with a throw error. If it receives some other message, let's say the ugly one, then it will do some more computation and things are okay. And actually, it will also check if it gets to the point of the receive and it has no message on its mailbox, and things will be okay. Okay, so all of you, I guess, can find out that this program, there is a way of crashing this program. I hope this is clear to everybody. Okay, so whoever doesn't see that, obviously hasn't programmed concurrent Erlang ever. Okay, what is not going to be very easy to answer for you is how many interleavings there are here that Concuerror needs to explore. What's the minimum number of interleavings that need to be explored? Anybody has a guess? Not Concuerror developer. But let's find out. Okay, so I actually have this program, and I'll show you how easy it is to run Concuerror. You run Concuerror by just typing Concuerror with the name of the module that you want to test. In this case, it's called foo, and the function that you want to also test. And this function better not take any arguments, because if it takes any arguments, then you have something else. You don't have only concurrency and non-determinism, you also have input non-determinism, and Concuerror doesn't generate inputs automatically. Okay? So you run this, and Concuerror does its magic automatically. So what has done here, it has instrumented the I/O lib, the gen server, the module foo that we run, the module Erlang, and the module bar that, recall, we were using to get the messages from the bad and the good and the bad and the ugly. And it has explored 5 interleavings in total, and one of them is erroneous. And it so happens that I have them here, and I can just, I can just show them how this is generated by Concuerror, by these options that it suggests. So the first interleaving, we are executing P continuously until it finishes. We are entering the receive, and no other process has ever sent messages at that point. So we are going to the timeout of the receive. So P exits normally, and then the P1 process does its job and sends its good message, but there is nobody to receive it at that point, and this exits normally, and the bad does the same thing. This is okay. Another interleaving is to start by executing the two spawns, the receive, and then have the other order of executing P1 and P2. Namely, P2 gets executed first and P1 gets executed second. There are some other uninteresting interleavings, and it's the last one, which actually is the one that causes the error, which is we are spawning the two processes here. Then we are not going to the receive, but we are going to say P2 that sends the bad message, and then we are going to the receive, which receives the bad and goes to the case where the error is thrown. Okay, so this executes all the interesting interleavings that it can find here, which are 5 in total. Okay, so we have these 5 interleavings. I showed them how they look. Okay, so Concuerror is a stateless model checking tool that runs and tests all possible conceptually interleavings. It detects abnormal process exits. You can put arbitrary assertions at any point in your code, and it will crash if these assertions are violated, and it reports all the events that could lead to the crash. So you can actually see how the processes get interleaved so that you get to the point where things crash. Now, you might be thinking, okay, is it really all the interleavings? I mean, there are really too many, right? So it turns out that actually not all the pairs of events are in arrays, so we only have to reverse or to check all the interleavings on things that race, not on, say, what process local executions are doing. And actually, we only need to explore one interleaving per class. And for this kind of audience, I will leave what a class of interleavings is unspecified, but take my word for it that there is a very clever algorithm that we have designed in Uppsala called optimal dynamic partial order reduction, which is the first algorithm ever to do partial order reduction in a dynamic way, in an optimal way. So the algorithm works at runtime. That's what a dynamic means. It reduces the set of interleavings that it has to explore by exploring by taking into account the partial order of all events, and it's optimal. It's provably optimal. It will explore only one interleaving in each class of something called Mazukevich traces that you should not really worry if you haven't heard it, and you probably don't want to hear about it. But believe me, this is a very strong algorithm. It has appeared in Popol some years ago, and it will appear within the year in JACM. This is very good stuff. So we now, on top of that, the tool comes with ways of actually exploring even less interleavings. So if you can put a bound, let's say that I want to only explore two points of preempting each process. I don't want to check that all my processes can be preempted everywhere. So you can put a bound, and you can select between various bounds. This is not a tutorial of the tool, so I will not explain all the possible bounding ways that you can bound stuff. But let's say we want to test our example here with B0. Do I need more? I'll find out. So rather than 5, it has explored only 1. Okay, because this is what you have to do if you don't allow any way of preempting, of any way of interrupting each process that is running. Or you can do with 1, and we'll find a bit more interleavings, 3 of them in total. Don't worry why there should be 3 or 4 or 5, but they are less than all the number of interleavings that you need without a bound. Now, in this particular case where you are using the bounding, you have absolutely no guarantee that you will find all the bugs. But you have a pretty good chance that if bugs exist, you will find them. Okay? So, let's go back to the CORFU adventure. So, what the engineers at VMware did is they designed a model for the system. Remember that they didn't even have a system, okay? They were designing the protocols at that point. So the model is that some servers, let's say 1 or 2, will suffice for what we're doing, undergo a chain repair to add 1 more server to the chain. And concurrently with that, there are some readers and writers. Let's say that 2 other clients try to write 2 different values to the same key. And we need 2 different values because we want to test that the write once property of CORFU is maintained. And then we have another client that wants to read a key twice. Why twice? So that we can see that there is no possibility that we can read first the new value and then the old value. Okay, that's a violation of linearizability. So the 2 properties, so of course, modeling CORFU is straightforward in Erlang. Really straightforward. You don't need to know, formal methods, and you don't need to know any modeling language and whatever else complicated. You just model the servers and the clients as Erlang processes. And all, of course, the requests you model as messages. And it so happens that here you need the following processes. You need a central coordinator, so that checks what's happening. It's like God here in some sense. You need the log servers of CORFU. 2 or 3 will suffice. You need the CORFU layouts process, a CORFU reading client, the 2 writing clients, and something that changes the layout and the data repair process. Okay, so you need quite a lot of processes, which actually makes the number of interleavings that you actually really need to explore quite many. And they tested with that one 3 different chain repair methods. The first one is the one that they knew it was buggy. They add the repair node at the end of the chain, the one I showed you. And they knew that there is a counter example that this doesn't work. In the other 2, they did not know whether these algorithms work. The second one, adding the repair node at the start of the chain, is the one that surprised Scott to the extent of writing in Twitter. Okay, because he thought that this would work, but the tool found a counterexample. And a third chain repair method, adding the repair node in the middle. And when you add stuff in the middle, you have to worry about whether you are adding to a chain with only one element or to a chain with more than one element, let's say 2. When you're adding in 2, it's easy, you just put it in the middle. When you're adding in the middle of something that's just 1, well, you need to do some logical split there. So you have to model this thing in some way. Okay, so they did this in Concuerror, and what has happened here? Let's see. Oops. So these are the numbers that we got. Actually, they did some small bugs in their modeling, which we have worked with them to fix them. So these are the numbers from the correct models. But basically, what's happening here, if you're using bounding, you find the bug very, very, very fast. In under a minute with the first method, and in just 7 seconds, Concuerror will find immediately, after exploring 65 only traces, with a second method, adding to the head. And you find no bugs for the third one. But that's with bounding. And I explained already that if you cannot verify things with bounding, because you only explore a subset of all the possible interleavings. So for the cases where there is a bug, the bounded exploration will find it very fast. So you don't have to think for hours around the whiteboard. You can just write a program, and in less than a minute, Concuerror will find the bugs in your algorithm for you. Now, what you cannot do in this way is if you have an algorithm that actually happens to work, and it doesn't have any bug, then you have to wait. Because in order for Concuerror to tell you that your algorithm is correct, it has to explore, using optimal DPOR, all the possible ways that it can reduce given the optimal DPOR algorithm, but still there might be too many. And as you see here in this table, there are many. So for example, to find the bug without bounding in the first method that we know it's buggy, the tool first needs to explore 3.5 million different interleavings. And that takes about 144 hours. This is on a standard desktop, and actually 5 years ago desktop. But sometimes the tool is actually very lucky. In its exploration for the second method, it finds it in just 26 seconds without bounding. And in the cases where the algorithm might actually be correct, it might take a while, like 750 hours, and the tool hasn't finished yet. Yes? Yes, unless you use the -K option, which surprisingly doesn't stand for Kostis, but it stands for keep going.
It's kind of pedantic, right?
Huh?
It's kind of pedantic.
Yes, but if you find the bug and you want to, it stops. It stops. Okay. No, it's more than that. It's all of them have many million states. Okay. So we have, what do we have so far? We have 2 algorithms that we know they don't work, and one that might have a chance to actually be correct. Now, that's where we actually started becoming interested in what we can do to actually optimize the tool. So I will now use the ugly message also. So this is a variation of the previous program, but we are spawning 3 different processes, P1, P2, and P3, and each of them is sending a different message. the good, the bad, and the ugly. And we have a slightly different receive. Actually, as a matter of fact, we have a combination of two receives here. One which just checks for good, and one that just checks for ugly. And in both cases here, actually, it's things go okay, but this is not the point here that things are okay. So the question is, how many interleavings does Concuerror need to check? And the previous version of Concuerror was actually needed to check 6 different interleavings, and you see them here. I will not explain them in detail. And this is because of the all possible ways that sending 3 messages can be received by 2 receives. Okay, and it needed to explore all the possible ways that messages can arrive. But this is where, I thought about it for a while and said, here we can do something better. This receive, the first one say, it's blocking. So it's only interested for the good message to come. We don't need to check all the possible ways of messages arriving in its mailbox. Okay? Because it's only interested in the good one. And similarly for the second receive, we are only interested in the ugly one. So it turns out that actually here, you can do much better. And you can optimize this type of thing and do some special modification of the algorithm that is still not in the distributed version of the tool, but we are working on making it part of the distribution. And this will cut down the number of different the number of interleavings that need to be explored, even with optimal DPOR, based on the fact that we know the patterns in receives. Now, treating this blocking receive especially avoids exploring a possibly exponential number of interleavings. And this is something that we did by hand for CORFU, because it was actually happening quite a lot in the model. It was the coordinator were receiving, this client is done, the other writer is done, many messages of that form. So that's one optimization we did in the tool. Then we did 2 model refinements, one based on conditional reads. Remember that we had 2 readers that were trying to read 2 values and check whether it's never the case that we read the new value first and then the old value second. So we avoided issuing read operations that were sure not to result in violations. So for example, if you ever read the old value first, it doesn't matter what the second one is, because it will not, the linearizability property will not be violated. So we changed the model to do this conditional read operation, and for technical reasons that I will not explain right now, we converted one of the processes to a net stable. Now, given these 2 small changes in the model that were done by hand, now we could actually verify method 3. And method 1, even without bounding, it finishes in just 19 seconds and finds the bug in just 19 seconds, even without a bounding. And method 3 is now verified. So we have actually verified using Concuerror that unless there is a bug in the model that was written by hand, the algorithm is correct. And this verification now finishes in 48 hours and needs to explore less than 4 million traces in total. That's it. So this is a talk about how we can use a tool that we never we designed for a totally different reason. We want to find concurrency errors in Erlang programs. But somebody clever enough like Scott went and used this tool to actually do verification of protocols and algorithms that were not even implemented. And he found the results surprisingly enough, surprising enough to actually spend some time in playing with the tool and refining them and encoding the all three different methods in the model, and just showing to his fellow colleagues that, hey, this algorithm that you think it might work, it doesn't have a chance because here's a bug, here's a situation that doesn't work. So Concuerror is a tool that can be used very effectively to test concurrent programs and concurrent algorithms in general. And occasionally it can even verify their correctness. I would like to just repeat that this is not quick check-like testing. Okay, here you get guarantees, which you do not get with quick check. Okay, or with proper for that matter. And Concuerror is a tool that has a lot of potential, both in the Erlang world and perhaps elsewhere. It's not something that you can use immediately. It requires some patience, and it requires to play a bit with it and get a feeling of how it works. But if you have some interesting algorithm that you are not sure whether it's correct or not, if you have a program that you really want to find out that it never crashes, it's an amazing tool to actually find you these things. If your program is crashing, Concuerror is very, very effective in finding it quickly. The problem is if your program doesn't crash. Okay, because it might take a long time to find out that it's not crashing. So all the code is available on GitHub, and of course you cannot remember this one by heart, but it will, the slides will be there at some point. And this is an open source project, so we welcome contributions of any sort. That's it. So, any questions? Yes. Yes. The question is whether you can estimate it good enough. Yes, there is this thing, and Concuerror does come with something that estimates the number of traces. The problem is that it estimates it only to the point that it has looked. Okay, only to the backtracking points that it knows about, not to the backtracking point that it has not seen yet. Okay, but it can get some reasonably precise. Not always, but sometimes actually this estimate works. It's an estimate, okay?
Any more questions? Yes.
But what you can do, just a moment. This is not answering your question. But what you can do is you can start with very small bounds, where it will actually finish very, 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 very fast, and get some estimate of your own how the numbers of traces increase by increasing the bound. Most likely, with a bound of 3 or 4, you will find the bugs. And you will have a good estimate yourself at that point, how many there will be with unbounded one. Yes, now.
Could it be parallelized?
Yes. Absolutely. And I have a student in Greece who is supposed to do that, but I don't know. Perhaps he will go vacations in Corfu and
Sit on the beach and have a nice time and parallelize it. Any more questions?
Thank you. Does it support testing processes that are running on different nodes, that is in a distributed mode, or is it only in one local node?
so currently not. It doesn't. It's only for a single node
Okay,
because it needs to take control of a scheduler.
okay,
And how to do that sort of thing with multiple nodes is not so clear. But it's really an engineering issue.
okay, okay. Thank you.
Any more questions? Yes.
So there is one more thing that I have not mentioned, and it's crucial, I think. So Concuerror and stateless model checking in general works only for programs that terminate, for tests that terminate. So if you have some test that doesn't terminate in some trace, Concuerror will actually explore it until it doesn't terminate. Okay, so but that's general. It's it's generally how you test programs. You will typically write tests that terminate. Yes.
Does it work if you have TCP/IP connections? So if you have some test that actually uses that to test your system?
So you need to do some, mocking or some way of, handling the external environment. In general, if your system is severely complicated and it's calling some things that are implemented in C, Concuerror doesn't know how to take control of C code and interleave it with the. So you need to have some way of doing this mocking for stuff. But yes, it supports pretty much all of the OTP libraries.
The case I'm specifically thinking about is if you're testing a server by actually writing a client directly in your tests.
Sorry, I cannot hear at all right now.
Sorry, is that better? If you're testing, for instance, a server by writing a simulated client directly in your test that uses the TCP protocol, for instance, would that sort of work?
If you are just testing the TCP protocol and you have modeled this sort of thing in Erlang, Concuerror is ideal for that. So you will actually find out any issues that you have there. I'm not sure that this is the question though, but we can take it offline. But if you want to just test an implementation of your TCP, the protocol that you have implemented, then it's very good for that.
Okay. Final question? Nope. We are done. Thank you very much.